A good day to all. We will be studying about a region of convergence in Laplace transform. Laplace transform is a transformation of a signal in time domain to a signal in complex frequency domain, which is called as S-plane. The S-plane is represented as sigma plus j omega, where sigma is the real part of the complex S-plane and omega is the imaginary part of the complex S-plane. We will be seeing a representation of this complex S-plane in the next slide. The Laplace transform has two parts, the expression and the region of convergence. The expression for Laplace transform of a continuous time signal is defined as x of s is equal to integration minus infinity to x of t e power minus st dt. However, this expression should always be accompanied with the region of convergence. So what is this region of convergence? Existence of Laplace transform x of s of a signal x of t depends upon the complex variable s as well as the signal itself. That is, when you obtain a Laplace transform of a signal, you should confirm that Laplace transform should exist or it should converge. If that Laplace transform does not converge, then there is no point in obtaining the frequency representation of that particular signal. Hence, it is always necessary to mention what is the region or what is the criteria under which the particular Laplace transform of a signal will converge. So this convergence depends upon the variable s as well as the signal itself. Both of them contribute to how the signal or the Laplace transform converges. So as we have seen already, the Laplace transform and the corresponding S-plane coordinates are given. The definition for ROC goes like this: all complex values of s for which the integral in the definition converges form a region of convergence in the S-plane. So this entire integration, when you find out Laplace transform, this integration value should be lesser than infinity. Okay, that means it has a finite value. In that case, we say that the ROC exists. ROC is determined solely by the real part of S. We know that S contains a real part sigma and imaginary part omega. But to determine ROC, we are bothered only about the real part of S, which is nothing but sigma. So imaginary part of S, which is omega, does not has any part in terms of convergence. So before going on into how to find the region of convergence, we should know how to represent the zeros and poles of the Laplace transform. So rational Laplace transform in general can be written as a ratio of polynomials of variable s. So any Laplace transform can be represented in the form of numerator divided by denominator, which has or which varies as a function of a variable s. So the general notation is given where n of s is the numerator polynomial and d of s is the denominator polynomial, and the numerator specifies the roots and the denominator specifies the poles. So roots of the numerator are called zeros and the roots of the numerator are called as zeros and the roots of the denominator polynomials are called as poles. Poles in the S-plane are indicated with a cross and zeros are indicated with a 0. The representation of x of s through its poles and zeros in the S-plane is referred to as pole zero plot. So the location of poles is very important in determining the region of convergence of Laplace transform, which in turn is used to determine the stability of the system. That is why poles play a very important role in Laplace transform in obtaining the region of convergence. They specify the boundary of that particular Laplace transform. So just we'll have a notation or look into the S-plane. So you can see that the S-plane consists of the x-axis is nothing but the real part sigma and the y-axis is the imaginary part j omega. So poles are represented by a cross and zeros are represented by a circle. So let us try to represent minus 2 plus j3. It's a rectangular form representation of a pole. So this central point is going to be 0. So minus 2 plus 3j will be obviously present over here. So this is marked as a pole. Once a pole is marked, the region of convergence is specified by the real part of S. So the real part of S here is nothing but minus 2, which is nothing but minus 2 over here. So the ROC we can, the initial representation of ROC can be represented by a strip line based on which the ROC of a Laplace transform can be obtained. It's nothing but a strip line which is parallel to the j omega axis. The central y-axis at 0 is called as j omega axis. The ROC has strips which is parallel to the j omega axis. Let us take another pole, minus 1. So it does not contain any imaginary part, so it can be represented simply on sigma. So it is minus 1 and the corresponding strip is also obtained. One more example to go, 4 minus j2. So 4 is on the positive side and minus j2 on the negative side, and the location of pole goes like this. So this is the way in which poles can be represented on an S-plane. Similarly, zeros can be represented as, so minus 2 minus j as represented over here. We are not representing as a strip line because zeros do not have any impact on the region of convergence of an S-plane. Just as an intuition, we are telling what is meant by zeros. Similarly, a 0, 1 is represented on the right hand side. So the strip lines, which are nothing but the real part of S, which is equal to sigma, specify the region of convergence. The region towards the left side of the imaginary axis. So this is the imaginary axis. The left side denotes the left half plane, and the region towards the right specifies the right half plane. So how can we explain now ROC? That can be explained with an example. So let us take the signal x of t equal to e power minus at u of t. The solution for this will be given in the consecutive videos. However, we will be looking or concentrating into the region of convergence in this particular video. When we find the Laplace transform this x of t, you need to apply the formula x of s equal to integration minus infinity to infinity x of t e power minus st dt. So when you do this Laplace transform integration, you will get a final answer x of s is equal to 1 by s plus a, which is very important now to consider for our ROC. So once you have here 1 by s plus a, you need to find out what are the poles. So the pole here is given as what? S plus a equal to 0. So the pole is s equal to minus a. So you can see that this integration will converge only if the real part of s plus a is greater than 0. So here you can see in this integration e power minus s plus a into t. Okay, so you have minus t. The integration limit is t value takes between 0 to infinity. So s plus a should definitely be positive. Only when it is positive, this integration will also turn out to be positive. If suppose s plus a value is negative, you will be getting e power plus t, and that will range to infinity, and your integral will not converge. Hence, we can conclude that the integral converges only when the real part of s plus a. Why we talk about the real part is s itself is a complex plane, right? It contains sigma and j omega. We are bothered only about the real part. So real part of s plus a is greater than 0, which can be written as sigma, which is a real part of s greater than minus a. So this can be represented as ROC over here. So you have sigma real part and imaginary. The pole, real part of the pole minus a is represented with a strip line. The ROC is real part of s greater than minus a. So for all values greater than minus a, note down it will not include minus a. Greater than minus a, this particular Laplace transform x of s is equal to 1 plus s plus a converges. So the ROC is real part of s greater than minus a. Let us take another example. So here we have taken the signal x of t equal to minus e power minus at u of minus t. So in the previous example, u of t was a right sided signal. When you plot u of t, it exists from 0 to infinity. U of minus t, it's obviously a left sided signal, because when you try to plot, you will know that it will extend from 0 to minus infinity. So when you perform Laplace transform, you will be getting the answer as the same answer, x of s is equal to 1 by s plus a, as you got for the previous one. However, when you look into this, the t value ranges from minus infinity to 0. So negative values hold for this t. So for this integral to converge, this s plus a value should be definitely lesser than 0. So this integration converges, or this integral converges only when real part of s plus a lesser than 0, which can be represented in an ROC here. So here our pole is s is equal to minus a. So s is equal to minus a, and it is represented over here, and it is real part of s lesser than minus a is obtained on the left hand side. So we can see that here minus a is taken over here because the value of a can either be positive or negative. The same pole can also be present on the left half of the s plane also. So this particular x of t converges, or this Laplace transform converges for a real part of s lesser than minus a. So when you compare the previous example and the next example, we can see that both the answers Laplace transform are same for x of s is equal to 1 by s plus a. What they differ is, for the previous one, it was the region of convergence greater than minus a, and for this example, the region of convergence is lesser than minus a. Thank you, students.